to be speaking about validity-based testing today. The slides are online and you can find them right there. I just wanted to put that up so you can actually follow the slides along if you want to. The slides are just marked down, so it's just a big text file. With that, let's get started. To start off the motivation, I need us to all agree that there is a situation that happens every so often, which is where you have invariants in your program. First off, maybe I should have a look. Who here writes Haskell? Has ever written Haskell? Is there anyone who cannot read Haskell? I'm going to be showing you quite a bit of Haskell code. If you can't read it, that's fine. You should probably be able to read it if you've ever done any maths, but it's good to know who has ever done maths. Sorry, who's ever done Haskell? Okay, so I can assume that most people can read what I'm going to be showing. What I'm going to be showing you is Haskell code, but all of the principles also apply in other languages, at least they should. And the library that I'm going to be presenting could probably also be rewritten in other languages. It just so happens that it's rather easy to do in Haskell, and I have not tried in other languages. So when we have invariants on our data types, we usually just write a comment that says invariant. There is this invariant on our data type. In this case, I can define a new type over integers that represents that this integer must be prime. And then the invariant says this prime that is contained within this constructor needs to be prime, or this integer needs to be prime for this prime to be valid. It would be much nicer and also, as it turns out, much easier to deal with later if we can actually explicitly define the code that will check whether this invariant holds true. And for that, we made this type class called validity, which allows you to specify with this function called isValid what it means for your value to be valid. For any value of your specific type that you declare to be an instance of this type class, you specify this is what it means for my value to be valid. And there are clear semantics for what this validity should, how this should behave. This should be an under approximation, meaning that for any invalid value, you must say that it's invalid. For any valid value, you should say that it is valid. As long as you keep to these semantics, you should be fine with respect to safety later. Now, we have some standard instances. For example, we could speak about the validity of lists if we could speak about the validity of the elements in the list. And because of these strong semantics that we've talked about earlier, it's really easy to define the validity of bigger types, given that the validity of that type is only defined as the validity of the subparts. And then, in fact, the library can write all the code for you. So you just say, this type should also have a validity instance. And then the entire implementation can be generated by just the last line on this slide. Now that we've defined what it means for a certain value to be valid, we can ask, is this value valid? But the problem is, once you find a value that is in fact invalid, you still are no closer to figuring out why it is invalid. So here we have a list of supposed primes, and it turns out this list is invalid, but we can't figure out why it's invalid based on just looking at the results. So there is a second function in this type class validity called validate, which allows you to figure out why something is valid or why it is invalid. And then if you look at the same list of primes I showed earlier, and you ask, why is this valid or not? And if it's not valid, why is it not valid? It will tell you the third element in the list, there is a problem, namely that there is an invariant that it has been violated, and this invariant is called prime. And then you can immediately see, oh, 6 is indeed not a prime. Now, everyone's still with me up until here. Now I'm going to be talking about how we apply this to testing, but I need to take a bit of a detour just to define some terms I will be speaking about in testing specifically. So when we look at the most basic kind of test, which I will assume to be a unit test, the idea is to run a piece of code. If the code crashes, we say that the test fails. If the code doesn't crash, we say that the test passes. You may say, well, there are some details with assertions, for example, and I will argue assertions are just a smart way to make your code crash. So the fundamental definition of a unit test is some piece of code, if it crashes, then it fails. If it doesn't crash, then we say it passes. So this is a unit test. We define property tests as something like a unit test, but now you also take an argument. This piece of code that now takes an argument, if it crashes, then it fails. If it doesn't crash, then we say the test passes. So we say that my test passes for 4 as an argument. So this is a property test applied to the argument 4. A random property test is similar, but now you will choose a random number. You will choose a number and run the test for random arguments that number of times. We say that a test passes if it passes for every one of the arguments. We say that the test fails if it fails for any one of the arguments. Then there is also exhaustive property testing, which is where you go over all the possible values of the certain argument that is the input. There is also specialized exhaustive property testing, which is where you take a subset of the input argument type and go over all of the values of those. As an example, we take the prime type I showed you earlier. You wouldn't give all possible integers as the argument, but all possible primes, which is, there are details to be gone over there, but that's the idea. Then there is also specialized random property testing, which is where you take random values of a special subset of the type you're looking at, or a given number of tests. We say that the test passes if for a certain number of values that are randomly generated from the subset of the type that you're looking at, all of the specific subtests pass. Now, how do we do this in practice? There is a type class called arbitrary in QuickCheck. QuickCheck is a property testing library that we usually use in Haskell, which specifies what it means to generate random values of a given type. So for any type that, oops, sorry about that. Now I can't see to turn it off. Any type that instantiates arbitrary, there exists a function called arbitrary, which can generate random values of this type. So arbitrary int means that there exists a function arbitrary which can generate random integers. Then we have a separate function called property, which allows you to turn any function that takes an argument that can be randomly generated and returns a Boolean to turn that into a test. And then the QuickCheck framework will take this function, generate random inputs, and test it for 100 cases. If it passes, then it passes. So this is one of the cases that I talked about earlier. Now, as soon as you go to specialized random testing, you get into trouble. For example, if you want to test functions that deal with primes, you run into issues. Specifically, how would you implement this instance of arbitrary for primes? There are some considerations. So the first thing you could do is only generate valid values. I will argue this is the wrong thing to do, because then you can never generate truly random values of the type prime. If you only generate valid values, you will never generate prime 6, for example. If this prime 6 ever occurs in your program and you haven't tested against it, you run into safety issues. You can also generate all possible values, but this may also be the wrong thing to do, because a lot of the functions you deal with are supposed to only deal with the valid values, and you don't care about whether they work for invalid values. So then you only want to test them for valid values. You can also say, oh, we can write separate generators for each of them, but this may also be the wrong thing to do, because now you lose the entire composability of these tests that you can possibly put together. For example, if you have a function called associative, which can test whether a certain binary operation is associative by generating random inputs and seeing if this holds. If associativity holds, and you have a separate one for identity, you can put these two properties together, given that the input can be randomly generated in the same way. But as soon as you start requiring separate generators, this is no longer possible. So we've solved this in a different way. We said we'll take two separate type classes. The first one is called gen unchecked, which allows you to explain how to generate truly unchecked arbitrary random values. ignoring all the invariants. As opposed to arbitrary, this has very clear semantics. All possible values that could exist at runtime should be, there should be a probability that they're generated. And because these semantics are so clear, now we can let the compiler completely generate the entire implementation of how to generate these values. The second type class that we've made is called GenValid. GenValid allows you to specify how to generate valid values. But again, because these semantics are so clear according to validity, we can generate the entire implementation. And in fact, the default implementation is rather simple. Generate an unchecked value. If it's valid, then return it. If it's not, try again. Now, as you may imagine, this can be rather slow. For example, if the predicate is expensive to calculate, for example, checking whether a number is prime, or if there aren't a lot of valid values that will be generated by unchecked, for example, primes. In that case, you can also write your own generator, which is what I've done in the second half of the slide. In this case, it says generating a random prime means either generating 2 or generating a value, making it odd, and then checking if it's prime. And an odd value is more likely to be prime than an even value is. That's the idea of the second generator. And you can make this as fast as you need it to be for your tests to run fast enough. Now that we have this entire framework of validity, gen unchecked, gen valid, and there's also gen invalid, which you may, it does exactly what you think it does. Now we can write more general testing combinators that will make the entire property for us. And we can just supply the functions that we want to have tested instead of having to define the entire property ourselves every time. So for example, if we have a function that could possibly fail by returning nothing instead of just a value, then we can now say this function fails whenever you pass it an invalid value as the argument. We can also say in the second example, whenever this thing succeeds, it will return a valid value. The third one is, whenever you give a valid value, it will succeed. So you can write very general testing combinators because there is now this framework. And in fact, all of these have been written already, so you just have to plug them into your test suite and start using them. But why stop there? You can make your properties not just for anything that fails or for specific things related to validity, but this also solves the problem of what to do if your functions only care about valid values. For example, the first combinator that I've written here at the top is called equivalent on valid, and it checks whether two different functions are equivalent, but it only cares about valid arguments. We don't care about whether these two functions are equivalent when you give them invalid arguments, so only valid arguments are generated and tested against. There is something similar for associativity. The third one says these are two functions that can both fail. They can both possibly fail in separate, different ways. But whenever they succeed, we want to make sure that if you apply them one after the other, then you get the original argument back. So you can write very, very general testing combinators to make the properties for you instead of having to write all of these properties yourself. But we can go even further. You can generate entire test suites by just looking at the type. This is assuming you already use a given test framework, you can start writing those test suites, generating those test suites. For example, here's an example if you use HSpec, which is where spec is an entire test suite. Now I can say, I wrote this custom instance for ordering my specific type. I want to make sure that this ordering still makes sense. So you say ord spec at my type, like so. Voila. Now I say ord spec at my type, and it will generate the entire test suite that makes sure that the ordering instance for your type makes sense. For example, equality needs to be reflexive. Inequality, oh sorry, this is not equality. This is larger than or equal to needs to be reflexive, greater than or equal to needs to be reflexive, smaller than needs to be anti-reflexive, etc., etc. You can also say, this only needs to make sense if we're dealing with valid values. For example, for doubles, we've chosen to define not a number to not be a valid double, in which case reflexivity holds for doubles, but only for valid values, etc. You don't have to stop there. You don't have to stop at simple or type-kinded types. You can also, for example, test whether the functor laws hold for your functor. For example, here is an example of the output of what you see when you say, check whether the functor laws hold for lists, and it will generate the entire test suite for you. These are the baked-in type classes, but you can also make these for custom libraries. For example, we have something similar for JSON instances. So you can say, I have a custom instance that defines how I want to serialize my value to JSON and back. Now, generate me the test suite that will check whether this makes sense. If you encode it and you decode it, then everything is all right. If you encode it, then it won't crash anywhere. If you decode it, then it returns an error instead of crashing, that kind of thing. Now, these are all the different kinds of tests that we can generate. So now we actually have to write very little code to test our entire does it make sense part of the code and not the business logic. So this is all of the code you have to write just to be able to start using these functions. So you have to say, this is my type. My type is a generic type, which means that we can deconstruct it on a library level as opposed to on a compiler level. It needs to be generatable for arbitrary values. We define validity. In this case, we don't define custom validity, so it just means use the validity of the subparts. And because this is all, and it needs to be possible to generate valid values. And now you can immediately start using all the functions that use your type and start testing them based on the standard properties that have been defined in the library. By the way, also all of the combinators have separate versions where you can supply your own generators. Here are some custom companion libraries that have all of these generators for entire test suites built in already for specific companion libraries that are used a lot. For example, for JSON, for binary instances, and for hashable instances. This is all defined for you already. That's all the slides I have, but I have a bit of a demo for you as well. Let me see if I can make that work. See the running of a test suite of a library that uses this kind of tests. I use this in production a lot, so let me just show you also what it looks like if you write one of those test suites. I say I have some settings and I have defined my own equality. So equality needs to make sense. I've made some custom generators. So I assert that generating valid values actually generates valid values. And I also have a custom JSON instance, so I need to make sure that these JSON instances make sense with respect to applying them back and forth. The next step, which we're already working on, is to do this all for you as well, which means we will have some custom code that will look at your entire library, look at all the custom instances you've defined, and then generate all of the does it make sense tests for you as well. When that's the end of the line for this kind of library. There is also a similarly interesting way of doing things that I've been working on a completely separate project, which is where we look at your code and figure out what your code does, propose to you, hey, is this what you think your code should do? And then generate the test for you as well. The entire idea of these kind of projects is to make testing your code easier than not testing your code, to make it cheaper to write correct software than it would be to write incorrect software. I'm more interested in the practical, how can we make this work, because acknowledging that we're dealing with humans aspect of dealing with this, as opposed to the industry way of, we know they don't use it, but it would be nice if they would, kind of way of doing things. This all makes sense for you. All right, this is all of the content I had. If there are any more questions, I'll be very happy to answer them. If you want to take me apart later, I will also be here for at least 5 more minutes after the talk. So I'll be very happy to answer your questions on that as well.